We rely on plastics to stop food spoilage and transport it safely. Yet that same protective barrier becomes a permanent marine pollutant when discarded. The global packaging sector has historically operated on a strict linear system. We extract finite fossil fuels, synthesize them into durable polymers, and dispose of them after a single use. This chart outlines mechanical recycling. Plastic is collected, shredded, washed, and melted for reuse. Food packaging breaks this loop. Organic residues contaminate the plastic. Under high heat melting, these biological remnants carbonize, severely degrading the resulting polymer. Because you cannot reliably mechanically recycle polymers that have touched food, the packaging sector had to find an entirely different approach. They turned to biology. The proposed solution was a massive shift toward a new class of materials, broadly marketed under the label bioplastics. But in 2015, the International Union of Pure and Applied Chemistry issued a clear recommendation to discard the word bioplastic entirely. The term is heavily ambiguous and creates a dangerous illusion for waste management. Instead, they required the industry to split the concept into two precise categories: bio-based and biodegradable. The distinction exists because of a basic chemical reality. Where the carbon in a polymer comes from has absolutely no bearing on how easily water and microbes can break its molecular bonds apart at the end of its life. To properly evaluate a polymer's environmental impact, industrial strategists must abandon marketing labels and plot these materials on a strict two-axis chemical matrix. This classification chart maps out the modern plastics landscape. The vertical axis represents the origin of the polymer's carbon material. It separates traditional fossil-based polymers on the left from bio-based polymers synthesized from renewable biomass like corn or sugarcane on the right. The horizontal axis plots the polymer's end-of-life mechanism. The top section contains durable polymers that heavily resist hydrolysis, while the bottom section contains biodegradable polymers, whose bonds are highly susceptible to being broken apart by water. Looking at the top right quadrant, we find bio-based but non-biodegradable polymers, like biopolyethylene and bio-PET. Harvesting carbon from sugarcane instead of crude oil lowers the initial supply chain emissions. However, the final polymerized carbon chain of bio-PE is physically and geometrically identical to standard petroleum-based plastic. It does not degrade, and it will persist in a marine environment for centuries. Returning to the chart, we can examine the exact inverse in the bottom left: petroleum-derived polymers that are fully biodegradable, such as PBAT. PBAT is synthesized entirely from fossil fuels, yet its ester bonds are highly reactive to water. This makes it exceptionally useful for products like agricultural mulch films, which are designed to break down directly in the soil after the harvest. Sourcing a polymer from a plant does not mean it will decompose in nature, and sourcing a polymer from an oil rig does not mean it will last forever. This leaves the bottom right quadrant, polymers that are both bio-based and biodegradable. Here we find the undisputed market leader, polylactic acid, or PLA. PLA dominates the food service industry. It provides excellent moisture barriers for fresh produce, is rigid enough for clamshell containers, and holds FDA approval for direct food contact. However, the classification biodegradable is conditional. This matrix shows the specific environments where degradation is proven. For PLA, notice that the soil, freshwater, and marine environment indicators remain gray. PLA requires a high activation energy to trigger its self-hydrolysis. Specifically, it must be processed in an industrial composting facility that maintains an internal temperature above 60 degrees Celsius with ample moisture. If a PLA clamshell container ends up in the ocean, where water temperatures hover around 20 degrees Celsius, it lacks the thermal energy required to break its chemical bonds. In that environment, it acts just like conventional plastic. A polymer is only truly compostable if the local municipal infrastructure has the thermodynamic capability to actively dismantle its chemistry. There is a polymer group that solves this dependency: polyhydroxyalkanoates, or PHA. Looking at the PHB variant on the grid, you can see proven biodegradability across both freshwater and marine environments. PHA is synthesized via bacterial fermentation and does not require industrial heat. It can actively metabolize in water at just 30 degrees Celsius. But chemical ideals crash into economic realities. Current PHA production costs are up to 10 times higher than conventional plastics. Additionally, its highly crystalline forms are exceptionally brittle, requiring extensive blending just to function as basic cutlery or straws. We have engineered polymers that can dissolve in the ocean, but their cost and mechanical limitations currently prevent them from scaling to meet global packaging demands. Industrial output reflects this. Global bioplastics capacity is projected to scale aggressively, from 2.18 million tons in 2023 to nearly 7.5 million by 2028. Within this expansion, thermally dependent PLA will command 44% of the biodegradable market, while marine degradable PHA remains a minority at 13.5%. To balance strict food safety requirements against the steep economic premiums of pure biopolymers, manufacturers are increasingly relying on hybrid blends, combining cheaper fossil-based PBAT with starch, or substituting partial renewable content to create bio-PET. The sheer volume of packaging needed for the global food supply ensures that cheaper, infrastructure-dependent polymers will dominate production over pure marine degradable options. Solving this paradox requires systems engineering. First, engineers calculate the barrier thresholds required by the perishable food, selecting a polymer to meet those demands. Second, this selection must be cross-referenced against the municipal waste capabilities in the precise region it will be discarded. Deploying PLA packaging into markets lagging massive, high-heat industrial composting centers guarantees these materials will simply accumulate in landfills alongside conventional plastics. We cannot print our way out of the plastic crisis with better labels or marketing terms. True circularity in food packaging is only achieved when polymer science, supply chain economics, and regional waste management operate as a single